Ever think about what's going on when you plug in your phone? I mean, like at the really basic level.
Most people don't, but it's pretty amazing.
It is. There's this whole hidden world of chemical reactions that are actually, well, they make electricity happen.
That's electrochemistry in a nutshell. It's all about the interplay between chemical reactions and electrical energy, how those reactions can produce electricity, and how, on the flip side, we can use electricity to drive chemical changes.
So, electrochemistry, I have to admit, when I saw the topic and all the stuff you sent over, I kind of thought back to high school chem class. Not exactly the most thrilling
I
memories.
get it, but trust me, this is way more relevant than maybe you remember.
Yeah, you were right about that. I mean, seriously, looking through this material, it's everywhere, from the batteries in our phones, laptops, electric cars even, to the way our brains send signals. It's all based on these same electrochemical principles. Pretty wild.
It is.
Yeah.
And, that's exactly what we're aiming for with this deep dive. We're going to take all this info you gave us and, distill it down to the really cool, essential stuff about electrochemistry. So you can not just know what it is, but really get why it's so important.
And it's way more than just like one little field of study, too, right? I was surprised to see how it pops up in these massive industrial processes, making all sorts of materials. But then it's also happening at like the tiniest level in biological systems.
You got it. So, to make sense of it all, we'll break it down. We'll start with something called electrochemical cells, which are basically like the tiny factories where these energy conversions take place. We'll see how we measure their potential, what happens when you change the concentration of stuff in those cells. Then we can get into some real-world examples you'll recognize, like batteries. Oh, and corrosion. That's electrochemistry at work too, unfortunately.
Okay, I'm ready to dive in. Let's start with these, what did you call them? Electrochemical cells? What are they exactly?
So imagine a setup where you can either generate electricity from a chemical reaction that wants to happen spontaneously, or use electricity to force a reaction that wouldn't normally occur on its own. That's what an electrochemical cell is all about. It's a controlled environment where we can either harness the energy released by a chemical reaction or put energy in to make a reaction happen that wouldn't happen naturally.
And there's this classic example, the Daniel cell, that kept popping up. Why is that one so important?
The Daniel cell is a great way to visualize a basic galvanic cell. Picture this. You have a zinc electrode dipped in a solution of zinc sulfate, and you have a copper electrode dipped in a solution of copper sulfate. We call these two setups half cells. Now, these half cells are connected by a salt bridge, which is this tube filled with a salt solution that lets ions move between the two compartments.
Okay, I'm picturing it, zinc in one, copper in the other. But why does anything happen? What makes it actually work?
The key is that zinc has this tendency to lose electrons, become a positive ion. And copper ions in the solution on the other side are like, hey, free electrons. They're ready to grab those electrons and become copper metal.
So it's like, I don't know, a game of electron hot potato where zinc wants to toss them and copper is eager to catch.
Exactly. And that flow of electrons from one side to the other, well, that's the electrical current we're talking about.
That's so cool. So the overall reaction, there was a chemical equation for it, right?
Right. So the overall reaction in the Daniel cell is Zn, solid zinc, plus Q2+, plus, which is the copper ion in solution, reacts to form Zn2+, plus, the zinc ion, and Q solid copper. It's a redox reaction, short for reduction oxidation.
Redox, I vaguely remember that. It's all about electrons being transferred.
Yep. You lose electrons in oxidation, gain electrons in reduction.
Got it. Now, you mentioned galvanic cells, but the materials also talk about electrolytic cells. Are those the same thing?
Similar but different. Think of it like this. In a galvanic cell, like the Daniel cell, the reaction happens spontaneously. It releases energy that we can capture as electricity. So batteries work. In an electrolytic cell, though, we're forcing a reaction to happen that wouldn't occur naturally. We're using electricity to make it go.
So kind of like pushing a boulder uphill. You need to put in energy to make it happen.
Exactly. And a great example of that is charging a battery. You're using electricity to reverse the chemical reactions that naturally happen when the battery discharges.
Makes sense. So charging a battery, that's an electrolytic process. And like regular batteries, those are galvanic.
Got it. So let's stick with galvanic cells for now. I mean, how do they actually turn chemical energy into electrical work?
Okay, so at the heart of it all is this concept called Gibbs energy, which basically tells you how much energy is available to do useful work in a system. In a galvanic cell, that available energy, the Gibbs energy, gets converted directly into electrical work. It's pretty amazing. So by measuring the voltage of the cell, we're essentially seeing how much that reaction wants to happen, energetically speaking.
Right. The higher the voltage, the more energetically favorable the reaction is.
And you mentioned earlier that we can think about these reactions as two separate half reactions.
Exactly. We have the oxidation half reaction where the zinc loses electrons. That happens at the anode, which is the negative electrode in a galvanic cell. And then we have the reduction half reaction where the copper ions gain electrons. That happens at the cathode, the positive electrode. And it's crucial that these two half reactions are happening in separate compartments, those half cells we talked about, connected by the salt bridge.
So two separate but connected processes. And I remember something about electrode potential. What does that mean again?
Think of it as a measure of how badly an electrode wants to gain or lose electrons. It's the potential difference between the electrode and the solution around it when everything is at equilibrium. We usually talk about the standard electrode potential, which is the potential when all the reactants and products are at a concentration of 1 mole per liter, what we call standard conditions. And just to make things easy, we always talk about standard reduction potentials.
Okay, standard reduction potentials. So if I see a table of these values, a bigger, more positive number means that species is more likely to be reduced to gain electrons.
You got it. It has a higher electron affinity, if you will.
And how does that relate back to the anode and cathode in our galvanic cell?
Well, the anode, where the oxidation is happening, that's where electrons are being released. So it ends up with a negative potential relative to the solution. The cathode, on the other hand, is where the reduction is happening. So it's attracting those electrons, which gives it a positive potential. And it's this difference in potential between the anode and cathode that drives the flow of electrons when we complete the circuit.
It's like a tiny electrical pressure difference pushing those electrons along. Now, I remember seeing this shorthand way to write out these cells that use vertical lines and stuff, right?
Yep, that's cell notation. It's a compact way to represent the whole cell. You write the anode on the left, cathode on the right. A single vertical line means there's a phase boundary, like between the solid electrode and the liquid solution. A double vertical line means there's a salt bridge. So, for example, if you have a cell with a copper electrode and a silver electrode, the notation might look like Q, solid copper, vertical line, Q2 plus, the copper ion, double vertical line, Ag plus, silver ion, vertical line, Ag, solid silver.
Okay, anode left, cathode right, single line for interface, double line for salt bridge. Got it. Now, how do we actually calculate the overall potential of the cell, the E cell, from those individual electrode potentials?
Easy peasy. E cell is just the reduction potential of the cathode, the right side, minus the reduction potential of the anode, the left side. So E cell equals E cathode minus E anode. Just make sure you're always using those standard reduction potentials.
Okay, E cathode minus E anode. So simple. Now, I keep seeing this EE thing mentioned, the standard hydrogen electrode. What's so special about that one?
The EEE is like our ultimate reference point in electrochemistry. We can only ever measure the potential difference between two electrodes, so we need one electrode to be our 0 point. And that's what the AE is. By definition, its potential is 0 volts at all temperatures.
And what does it actually look like, this AE?
It's pretty basic, actually. You have a platinum electrode coated with this finely divided platinum powder called platinum black. That electrode is immersed in an acidic solution where the concentration of hydrogen ions is 1 mole per liter. And you bubble hydrogen gas around the electrode at a pressure of 1 bar.
So we can hook up any other half cell to this SEG, and the voltage we measure will tell us the standard electrode potential for that other half cell, right?
Exactly. Because the SEE is always 0 volts, the measured voltage is all due to the other half cell.
Makes sense. And the signs of those potentials, the pluses and minuses, what do those tell us about the reactions?
A positive standard reduction potential means that the species is more easily reduced than hydrogen ions. And a negative one means it's less easily reduced.
So copper ions like to gain electrons more than hydrogen ions do, and zinc metal is more likely to lose electrons than hydrogen gases.
Right, and that actually explains why the Daniell cell works. Zinc gives up its electrons, copper ions grab them, and we can even calculate the standard cell potential for the Daniell cell using those values.
Oh yeah, how do we do that?
So the standard cell potential, E0 cell, is just the standard reduction potential of copper minus the standard reduction potential of zinc. So 0.34 volts minus negative 0.76 volts, which gives us 1.0 volts.
So the Daniell cell has a standard potential of 1 volts. That's a positive number, so it's a spontaneous reaction.
Exactly.
Now there's this other thing I saw, inert electrodes. They're like platinum or gold.
Yeah, inert electrodes, they're really useful when neither the oxidized nor the reduced species in a half reaction is a solid metal.
So they're not really part of the reaction itself?
Not chemically, no, but they provide a surface for the electron transfer to happen. Think of the SHE. You need that platinum electrode for the hydrogen gas to be oxidized or the hydrogen ions to be reduced.
Right, right. Okay, so these standard electrode potentials, they seem really important, but is it just about comparing different reactions?
It's way more than that. We can use them to predict whether a reaction will be spontaneous or not.
Hmm.
If E naught cell is positive, the reaction will happen on its own. We can also use them to compare the oxidizing and reducing strengths of different species, like fluorine gas, F2. It has a huge positive standard reduction potential, so it's a really strong oxidizing agent. It loves to gain electrons. On the other hand, lithium metal, Li, has a really negative potential, which means it's a powerful reducing agent. It wants to get rid of its electrons.
Wow, so these potentials are packed with information, but what about when things aren't at those standard conditions? What if the concentrations are different?
That's where the Nernst equation comes in. It lets us calculate the potential of an electrode or a whole cell, even when the concentrations aren't 1 mole per liter.
So it's like a correction factor.
Exactly.
Okay, so what does it look like, this equation?
So for a general reaction where you have a metal ion, Mn+, in solution gaining electrons to become a solid metal, M, the Nernst equation is, well, it's a bit long. But basically it says that the actual potential of the electrode equals the standard potential. Mine is this term that depends on the temperature, the number of electrons transferred, and the concentration of the metal ion in the solution.
So the voltage we actually measure depends on both that standard potential and how much of the stuff is actually in the solution.
Right. So let's think about our Daniell cell again. If we make the copper ion concentration higher, the cell potential goes up. If we increase the zinc ion concentration, the potential goes down.
So more copper ions means there's more pull for those electrons, more driving force?
Exactly. And more zinc ions means the reaction is less likely to go forward.
That makes sense. No, there's a simpler version of the Nernst equation for room temperature, right?
Yeah, at 298 Kelvin, which is pretty much room temperature, the equation simplifies a bit. For the Daniell cell, it becomes E cell equals E naught cell minus 0.059 divided by N, which is the number of electrons transferred, times the log of the zinc ion concentration divided by the copper ion concentration.
Okay, I think I can handle that version. So this Nernst equation is telling us how far away from equilibrium our cell is, right?
Absolutely. And speaking of equilibrium, there's a really cool connection between cell potential and the equilibrium constant of a reaction.
Oh, yeah. Because at equilibrium, the cell potential should be zero, right? There's no net flow of electrons anymore.
You got it. And if you plug in 0 for the cell potential and Kc for the reaction quotient in the Nernst equation, you get an equation that relates E naught cell directly to Kc. It's pretty neat.
So if we know the standard cell potential, which is easy to measure, we can figure out how far the reaction will go, even if it's hard to actually measure the concentrations at equilibrium.
That's the power of electrochemistry. For instance, if you do the math for the Daniell cell, you find a Kc value that's like 10 to the 37th power. That's a huge number, which means the reaction essentially goes to completion.
Wow, that's a really strong reaction then. Okay, we've talked about potential, equilibrium. But what about Gibbs energy? How does that fit into this whole picture?
Well, remember how we said that galvanic cells convert Gibbs energy into electrical work? Turns out there's a direct relationship between them.
Oh, yeah. So we can actually calculate the Gibbs energy change for a reaction just by measuring the cell potential.
Exactly. The equation is delta Rg, which is the change in Gibbs energy, equals negative n, the number of electrons transferred, times F, the Faraday constant, times E cell.
And the Faraday constant is just the charge of 1 mole of electrons, right?
Right, about 96,500 coulombs per mole.
Okay. And under standard conditions, that equation becomes delta Rg naught equals negative NFE naught cell.
Yep. So for the Daniell cell, we can plug in the numbers, and we get a delta Rg naught of about negative 212 kilojoules per mole. The negative sign tells us the reaction is spontaneous.
And that all ties back to equilibrium too, right? Because delta Rg naught is also related to Kc.
It is. It's all connected. And if we want to calculate the equilibrium constant for the reaction between copper metal and silver ions, which is another classic example,
Right.
you could do that using the standard cell potential. It turns out to be a really big number too, which means that reaction also goes pretty much to completion.
It's incredible to think that all this complex chemistry is happening every time we use a simple battery.
It is.
Okay, let's switch gears a bit now and talk about how electricity actually flows through solutions, something called conductance. I remember seeing terms like resistance and conductivity. Can we start there?
Sure. So when we talk about how well a solution conducts electricity, we're essentially talking about how easily charged particles, the ions, can move through it. And just like with a metal wire, there's resistance, which is how much the solution opposes the flow of charge, and conductance, which is the opposite, how easily the charge flows.
So resistance is like a traffic jam for ions, and conductance is like smooth sailing.
Perfect analogy.
Hmm.
And then there's resistivity and conductivity, which are basically like the inherent properties of the solution that determine how resistant or conductive it is.
Okay, so resistance and conductance are for a specific setup, and resistivity and conductivity are more general.
Exactly. And just so you know, IUPAC, the folks who decide all the chemistry naming stuff, they recommend using resistivity and conductivity more than the others.
Good to know. So how does the actual size and shape of the solution affect all this?
Well, the resistance of the solution is directly proportional to the distance between the electrodes. The farther the ions have to travel, the higher the resistance. And it's inversely proportional to the cross-sectional area of the solution between the electrodes. A wider path means lower resistance.
So a longer, narrower path means more resistance, which makes sense. Now, we have metallic conductance, where electrons carry the current in a wire, and we have electrolytic conductance, where ions do the job in solution. What are the main differences between those two?
The biggest difference is that in metals, it's those free electrons that move, and the metal itself doesn't change chemically. But in electrolytic conductance, it's the ions that are moving, and that movement is directly tied to chemical changes happening in the solution.
Right, because the ions have to actually reach the electrodes to gain or lose electrons.
Exactly. And another key difference is how temperature affects them. In metals, usually higher temperature means lower conductance because the metal atoms vibrate more and kind of block the flow of electrons.
Kind of like more obstacles for the electrons to dodge.
Yep. But in electrolytic conductance, it's usually the opposite. Higher temperature means higher conductivity because the ions move faster and the solution becomes less viscous.
So it's like heating up the solution makes it easier for those ions to swim around.
Right. And there are other factors that affect electrolytic conductivity too, like the type of electrolyte, how big the ions are, how much solvent is around each ion, and of course, the overall concentration of the electrolyte.
So lots of things to consider. Now, how do we actually measure the conductivity of a solution? It's not as simple as just sticking a multimeter in there, right?
Nope, not with direct current anyway. If you use DC, you'll start electrolyzing the solution, and the concentrations will change, messing up your measurement.
Yeah.
So we use alternating current, AC, to avoid that. And we use a special container called a conductivity cell.
What's so special about that?
It usually has 2 platinum electrodes coated with this fine platinum powder called platinum black, which increases the surface area. And each cell has a cell constant that relates its physical dimensions to the measured resistance.
So if you know the resistance and the cell constant, you can get the conductivity.
Exactly. And to get that cell constant, you first measure the resistance of a solution with a known conductivity, like a standard potassium chloride solution. Once you have the cell constant, you can measure the resistance of any solution in that cell and calculate its conductivity.
Okay, so it's all about calibration. And I remember seeing something called molar conductivity. How is that different from regular conductivity?
Regular conductivity, kappa, tells you how well a solution conducts electricity in general. Molar conductivity, lambda, takes into account how much of the electrolyte is actually in the solution. It's basically the conductivity divided by the molar concentration of the electrolyte. So it tells you the conductivity per mole of electrolyte.
So if you dilute a solution, the regular conductivity goes down because there are fewer ions per unit volume. But the molar conductivity might actually go up because each mole of electrolyte now has more space to move around in.
Exactly. You're getting it. And if we keep diluting until we reach hypothetically infinite dilution, the molar conductivity we get is called the limiting molar conductivity, lambda nautum.
Limiting molar conductivity. So that's like the maximum conductivity you can get from 1 mole of that electrolyte.
Exactly. And for strong electrolytes, the ones that dissociate completely in solution, we can usually get this limiting value by extrapolating from measurements at lower concentrations.
But not for weak electrolytes, right? Because they don't fully dissociate.
Right, and that's where Kohlrausch's law comes in handy.
Okay, Kohlrausch's law. Tell me about it.
Well, Kohlrausch was this clever guy who figured out that the limiting molar conductivity of an electrolyte is just the sum of the conductivities of its individual ions. Like, the limiting molar conductivity of sodium chloride is the sum of the limiting molar conductivity of sodium ions plus the limiting molar conductivity of chloride ions.
So the individual ions each contribute a fixed amount to the overall conductivity.
Right. And it doesn't matter what the other ion is. So
Yeah.
we can use this law to figure out the limiting molar conductivity of weak electrolytes,
Mm.
which is hard to measure directly.
That's so clever. And is that all it's good for?
Nope. We can also use it to figure out the degree of dissociation of a weak electrolyte.
Yeah.
How much of it actually breaks apart into ions in solution.
And once you know the degree of dissociation, you can get the equilibrium constant.
Yep. So we can use conductivity measurements to learn a lot about the behavior of electrolytes in solution.
That's amazing. Okay, let's talk about electrolytic cells now. Those are the ones where we use electricity to make a reaction happen that wouldn't go on its own, right?
Right. We're putting energy in to force the reaction.
So like electroplating.
Exactly. Electroplating is a great example. You use electricity to deposit a thin layer of metal onto another metal object.
And how does that work?
Well, you have two electrodes immersed in a solution containing ions of the metal you want to deposit. The object you want to plate is the cathode, the negative electrode, and you apply a voltage across the electrodes. The positive metal ions in the solution are attracted to the cathode, and they gain electrons, becoming solid metal atoms that deposit onto the surface.
And what's happening at the other electrode, the anode?
At the anode, something has to be oxidized to provide those electrons. If it's an inert electrode, like platinum, then water molecules might get oxidized to oxygen gas. But if the anode is made of the same metal you're plating with, then the anode itself will dissolve, releasing metal ions into this solution.
So it's like a continuous supply of metal ions.
Exactly. And this is how we refine metals too. Like with copper, you start with an impure copper anode, and as you electrolyze the solution, pure copper is deposited onto the cathode.
So it's purifying the copper. That's
Yeah.
really cool. And this electrolysis stuff, it's not just about plating or refining, right?
Right. It's used to make a lot of important chemicals too, like chlorine gas, which is used to disinfect water, and sodium hydroxide, which is used in a ton of industrial processes.
So how do we know how much stuff we'll get from electrolysis?
That's where Faraday comes in. He did a ton of experiments with electrolysis and came up with some really important laws.
Faraday's laws. Remind me what those are.
His first law says that the amount of stuff produced or consumed at an electrode during electrolysis is directly proportional to the amount of electricity you pass through the cell. More electricity, more product.
Makes sense. What about the second law?
The second law says that if you pass the same amount of electricity through different cells, the amounts of different substances produced are proportional to their equivalent weights. So it's like a recipe for how much of each substance you'll get.
And there's this unit of charge named after him too, right? The Faraday?
Yep. 1 Faraday is the charge of 1 mole of electrons, which is about 96,500 coulombs.
Okay, so if we know the current and how long we run the electrolysis, we can calculate the total charge. And then, using Faraday's laws and the balanced chemical equation, we can figure out exactly how much of each product we should get.
You got it. It's all very quantitative.
Okay, that makes sense. But what about when you have multiple ions in the solution? How do we know which ones will actually react?
That's a great question. The products of electrolysis depend on a few things. First, what's in the solution, obviously. Second, the type of electrodes you're using. And third, the standard electrode potentials of all the species involved.
So it's like a competition between different possible reactions.
Exactly. The reaction that's most favorable, thermodynamically speaking, is usually the one that will win. But sometimes there are kinetic factors that can come into play too, like overpotential, which is that extra voltage you need to apply sometimes to get a reaction to go at a decent rate.
Oh, right, overpotential. That can throw a wrench in things.
It can. So predicting the products of electrolysis can be tricky. But with a good understanding of thermodynamics and kinetics, we can usually figure it out.
It sounds like a lot to consider. Can you give me an example?
Okay, imagine you have an aqueous solution of sodium chloride. So we have sodium ions, chloride ions, and water molecules. Now, at the cathode, sodium ions could be reduced to sodium metal. The water molecules can also be reduced to hydrogen gas.
Or which one is more likely?
Well, water reduction is more favorable because its reduction potential is less negative than sodium's.
So we'll get hydrogen gas at the cathode.
Most likely, yes, unless you have some really specific conditions. Now, at the anode, chloride ions could be oxidized to chlorine gas, or water molecules could be oxidized to oxygen gas.
Another competition.
Right, and this one's trickier. Based on standard potentials, oxygen formation seems more favorable. But the overpotential for oxygen formation is often high, so it can be sluggish. And if the chloride concentration is high enough, you'll probably get chlorine gas instead.
That's really interesting. So the actual products can depend on both thermodynamics and kinetics. And what about if the electrodes aren't inert?
Ah, that's another twist.
Mm.
If you use reactive electrodes, they can participate in the reactions themselves. For instance, if you electrolyze a solution of silver nitrate using silver electrodes, the silver anode will dissolve, releasing silver ions into the solution.
That makes sense. So predicting the products of electrolysis isn't always straightforward, but it's all based on these fundamental principles we've been talking about.
Exactly.
Okay, let's move on to something a little more familiar. Batteries. They're everywhere these days. What are the main types?
We can broadly divide batteries into two categories.
Yeah.
Primary and secondary. Primary batteries are single-use, like the ones you find in your TV remote. Secondary batteries are rechargeable, like the one in your phone or laptop.
Let's start with the basics. How does a simple dry cell battery work?
Think of a typical AA or AAA battery.
Hmm.
That's a dry cell, also called the Leclanche cell. It has a zinc container, which is the anode, and a carbon rod in the middle, which is the cathode.
Okay, so the outside is the negative terminal.
Right. And around that carbon rod, there's a paste of manganese dioxide and carbon. Then the space between the zinc and the cathode is filled with a paste of ammonium chloride and zinc chloride, which is the electrolyte.
So when the battery is connected, what's actually happening?
At the anode, the zinc is oxidized, meaning it loses electrons. At the cathode, the manganese dioxide is reduced, meaning it gains electrons. The overall reaction is a bit complex, but the electrons flow through the external circuit, powering your device.
And you can't recharge these, right?
Not really. The reactions aren't easily reversible. Once the zinc is used up, the battery is dead.
Okay, so that's the dry cell. What about mercury batteries? I feel like those are less common now.
They are. They used to be popular for things like watches and hearing aids because they have a very stable voltage.
How do they work?
They're similar to dry cells, but they use a zinc-mercury amalgam for the anode and mercury oxide for the cathode. The electrolyte is potassium hydroxide, and the overall reaction is, well, it produces zinc oxide and mercury.
Okay, so those are the single-use batteries. What about the rechargeable ones, the secondary batteries?
The most common example is the lead-acid battery, the one you find in most cars.
Oh, yeah. Those are heavy. What's inside those things?
They have lead plates for both the anode and the cathode. The anode is just lead, and the cathode is coated with lead dioxide. And the electrolyte is a solution of sulfuric acid.
And how do they work?
During discharge, the lead at the anode is oxidized to lead sulfate, and lead dioxide at the cathode is reduced to lead sulfate. And the sulfuric acid gets used up in the process.
So when you charge the battery, you're basically reversing that reaction.
Exactly. You're converting the lead sulfate back to lead and lead dioxide and regenerating the sulfuric acid.
That's pretty neat. What other kinds of rechargeable batteries are there?
Well, there are nickel-cadmium batteries, but they're not as common now because of environmental
Oh,
concern.
yeah, cadmium is not good stuff.
Right. And then there are nickel metal hydride batteries, which are popular for things like power tools. And of course, lithium-ion batteries, which are used in everything from phones to electric cars.
Lithium-ion, those seem to be the hot technology now.
They are. They have a high energy density, which means they can store a lot of energy for their weight. And they don't have a memory effect, which means you don't have to fully discharge them before recharging.
So all these different batteries, they're really just clever ways of using electrochemistry to store and release energy. Now, what about fuel cells? Those are different, right?
Fuel cells are like batteries, but they don't store the fuel internally. They need a continuous supply of fuel and an oxidizing agent, usually oxygen from the air.
And they just keep going as long as you feed them.
Yep, and they're much more efficient than burning the fuel directly.
That's cool. What are some common fuels for fuel cells?
Hydrogen is the most common, but you can also use methane, methanol, and even some other organic compounds.
And the hydrogen fuel cell, that's the one that produces only water as a byproduct, right?
That's the one. It's very clean. At the anode, hydrogen is oxidized to protons and electrons. At the cathode, oxygen reacts with those protons and electrons to produce water.
Sounds pretty simple. Why aren't we using them for everything?
Well, there are some challenges. Storing and transporting hydrogen safely can be tricky, and the fuel cells themselves can be expensive to manufacture. But there's a lot of research going on to overcome these challenges because they have huge potential for a cleaner energy future.
I hope they figure it out.
Yeah.
Okay, let's end on a slightly less positive note. Corrosion, rust, tarnish, all that unpleasant stuff. That's electrochemistry too, isn't it?
Sadly, yes. Corrosion is essentially an electrochemical process where a metal reacts with its environment and is slowly destroyed.
And rust, that's the most common example, right?
Yep. Iron rusting is a classic electrochemical reaction. It happens when iron is exposed to both water and oxygen.
So it needs both.
Yep. And what happens is some areas on the iron surface act as anodes, where the iron atoms lose electrons and become iron 2 ions. Exactly. And those electrons flow through the metal to other areas, which act as cathodes.
And what happens at the cathode?
At the cathode, oxygen from the air reacts with water and those electrons to form hydroxide ions.